Very big pleasure to demonstrate to you some of our Commission's current policy and also some of our thinking behind what is asked to do for the Commission. So many of you might have read this 188 pages that we published earlier this year. So the consultation period closed on the 28th of March. We received over 15,000 different submissions across Aotearoa, and very, very grateful from many, many different demographics, especially the youth voices. So between myself and Antonia tonight, we're going to present to you what is unpacking some of our analysis while we were developing our draft report, and also sharing with you what are some of the analysis and the evidence that when we went through our last 18-month journey. So some of those might be more interested in different sectors. Some of you might be more interested in the modeling. So the slide pack here is providing you an overview. I'm happy to answer any questions, perhaps during the break. So myself and Antonia, we're going to go through the whole slide pack in quite a speedy rate tonight. So first of all, I would like to divided into different subsections. So the first section is how we went about it. So the approach here demonstrates our three different lenses when we are advising carbon budgets, particularly the inputs, the analysis, and the advice that as the output from this. So this is quite a neat diagram to accumulate all these different pieces of work. So we started with actions that reduce our emissions, identifying what are the opportunities. Look at the long-term scenarios between now and 2050 and beyond. Then we cross our path to our 2035, which is the three carbon budgets that we are asked to present and recommend to the minister. Then we also consider the different aspects across our social, economical, and environmental. And then finally, we put our recommendations on policies. So all this journey took more than 18 months. And for the Commission, during this setup phase, it was a very challenging and also a lot of excitement that underpinned that. So testing the budget can also deliver many, many manageable things. And I'm going to share with you. And then later today, we're going to present the level of budget and the emissions reduction plan that relates to the first carbon budget, which is 2022 to 2025. So many of you might have come across the profile in Aotearoa. So this is based in 2018. So we split up into two different gases, so long-lived and biogenic methane. And this language is throughout our report. And some of you probably more relatable to the long-lived, some of you might be more relatable to the biogenic methane. The two boxes underneath is those targets described in the Act. So the net zero by 2050, including forestry, and the 10% reduction by 2030 from 17, and then a further reduction of 24 to 47% by 2050. So let's look at the long-lived gases. So this is one of our scenarios that we put under the current policies. What it says is that if we split and then restack all the sectors all together, starting from waste and F gases, agriculture, heat industry power, building, transport, those are all the economic sectors. And then underneath these are the two different forestry types. So the black line shows that the net emission and also the dot is 2050. It shows that under the current policy setting, it is unlikely that we will meet the 2050 target. If we extend that out to the currency approach, that if we put some more of the considerations of different or more broader policy context, then we are likely to beat the 2050, and some of these will be later in the slides presentation. So the next slide is show how we go about it. So we had very good discussions with the Commission talking about the principles. And this is something that a lot of the voices that we heard during our consultation and engagement. So what we are focus on the decarbonizing the economy, create different options, and avoid unnecessary costs. These are the key parts that build our evidence and also our body of work. And the two key transformations to meet the 2050 is to decarbonize the sources of long-lived gases and also build a long-term carbon sink through the new native forests. So let's looking into the net zero. So through our modeling work, these packages of policy recommendations demonstrated it is possible not just meeting the 2050 target, but go below the target. If you look through extending the 2050 cycle, when it goes out to beyond 50, so that means that with no further exotic forest plantation after 2050, there is a possibility that we bounce back up. So that means that there is a balance here of what the native plantation role play in our carbon budget. And we estimated that with 5,000 hectares per year, that will be some of the achievements that we'll be able to meet. So if we look at the modeling in a different lens, so this one shows that our path to 2035 sits compared to our scenarios. So the gray area are the different sensitivity cases that we run across. And the main baby blue line is the path that we recommend in our draft advice report. So that means that between 2020 to 2025, we'll still see a plateau of emissions profile. And the emissions reduction we'll start to see is from 2027 onwards, and then a steeper and more accelerated rate from 2030 onwards. So, and this is the breakdown of those different sectors, how we're going to go about it. So we have is the base year in 2018 of 45.7, and then the current policy settings that I showed you the path earlier on with the 4 different roles, and that will still meaning that in 2035 we have 27.4 million tons in net emissions. Now let's add some more to this. So we're adding more in terms of the reduction in the buses and transport, and also the different types in the aviation and shipping, more in the building, electrification, fossil fuel, and also the other sectors. So that is gradually stepping down our emissions budget, and finally in the agriculture and also the F gases. So you will see some of those pieces that come out from our draft advice in different sector by different chapters. And then finally, the net emissions will come into approximately 13.1 million tons. So I'm going to hand over to Antonia, where she will continue this discussion and also breaking down further into the different sectors.
Thank you very much, Kenny. I'm going to continue at also quite a rapid pace, and I'm going to borrow my helpful laptop here because my background is in heat industry and power. Being told to stand between the chairs. Yeah, my background is in heat industry and power, and I have to talk about biogenic methane, which I am not qualified to do. So at pace then, what you have here is a chart showing you under different scenarios what could happen to biogenic methane within Aotearoa in order to hit the 2030 target. And what this shows you is basically that we have a range of options. Moving swiftly on, the path does not rely on new technologies in order to hit the target. And in slightly more detail, this is how we reduce biogenic methane. So essentially what happens is we don't rely on the mythical, I shouldn't say that in public, on the vaccine. What happens is under current policy, stock numbers from dairy, sheep and beef decline by 8 to 10%, and this is due to a mixture of freshwater reform, land use change and on-farm practices. But the farmers today can make improvements to their productivity and reduce emissions. It means fewer animals producing the same amount of milk and meat that they do now. And at this point, I will cease talking about agriculture. So what does the path involve for each sector? So this takes Kenny's water flow diagram that she finished with and unpacks it in a bit more detail for you. So electrifying the transport system. Oh, sorry, don't want to miss that. So this unpacks some of the input assumptions that we put into the model. So what you see here is household travel distance reducing by 7% through things like more compact urban form, changing how we travel. So that's the share of distance traveled by walking, cycling, and public transport increasing by 25%, 85%, and 120% respectively by 2035. And then not shown here, freight. We assume 4% of freight ton kilometers be switched from road to rail and shipping by 2030. Obviously, the caveat to all of this is that we're currently looking through everybody's submissions, and all of this is up for debate and changing as we go through the evidence that everyone has provided to us, and we rerun the models. So these aren't our final assumptions, and these will change as we produce the final evidence and advice reports. So in terms of EV assumptions, we did assume a phasing out of light internal combustion engines by 2032 in the modeling, and that half of all light vehicle travel is electric in 2035. In the path, medium and heavy trucks are slower to electrify, and that's because current battery technology lags a bit behind for those heavy vehicles and for the distance that heavy vehicles need to travel. So of all the trucks imported in 2030, 15% of medium trucks and 8% of heavy trucks would be electric. And by 2035, those increased to 84% and 69% respectively. Into my happy space. Reducing coal and gas use in buildings. So we saw a natural capital recycle of moving out of using gas and coal in the building stock. So particularly for new buildings, ceasing to install gas, and then for existing building stock moving out of using gas as on sort of a 20-year effective natural capital recycle. So basically, as the gas use in buildings, the appliances and stuff turn over on a 20-year cycle, those would move over to being electrified. So improving efficiency in fuel processing and fuel use in process heat. This is mostly to do with the food manufacturing sector. So this is things like dairy factories using coal boilers mostly. And we gave them a choice of options within the modeling between biomass and electrification. Generally, biomass seems to be a cheaper option in the early years, and then electrification happens in the later years, and that's sort of what you see coming through in this result. And energy efficiency also happening here as well. So it's the equivalent to one large dairy plant converting to wood pellet a year. And gas switching tends to start around 2030. So this is the electrification story. So what you see here is TY switching off in our modeling around 2027, although that might change. And then rapid electrification required as the transport demand feeds through into the model. So we see about a 3% per year growth rate after as that sort of that gray line comes up. Okay, and this is just what it means in terms of the generation build. So you can see quite a lot of gas closure in the early years. So that's the pale blue lines underneath the axis, and then quite a lot of wind and solar. And we're actually relatively agnostic towards which renewables it is that gets built. We're tech agnostic there, but in the model, it just happens to be wind that gets built. Okay, back to my unhappy place in terms of what I'm qualified to talk about. Planting more forestry with a focus on natives. So we see around 12,000 hectares of new native forests being established in 2021, and the path sees this ramp up to 25,000 hectares a year from 2030, and in total close to 300,000 hectares of new native forests are established by 2035. And in our path, exotic afforestation continues on the trajectory expected under current policies up until 2030, averaging around 25,000 hectares per year. Perfect. So towards the end, reducing waste to landfills and improving gas capture. So this is moving into the circular economy space. So our path sees a reduction in the amount of waste generated, and then a focus on reducing the amount of organic waste that goes to landfill. And it sees a decrease of about 23% from 2018 to 2030. And so we see some minor improvements in landfill gas capture, and that's where we've had quite a lot of feedback from stakeholders on that. So it'll be interesting to see what changes in the final results. And that's actually it from me. So thank you very much, and we look forward to everyone's questions. Are you up next?
How's that? Okay. Just to reiterate, we are taking questions at the end, but as we go through, we will take the opportunity to ask a couple of questions, particularly of the upvoted. So if you see any questions that you'd like to be asked to our presenters throughout the course of the evening, take the opportunity to go onto Pigeonhole and upvote them. We do have a question here from someone in the room. What level of support is the government willing to offer for retaining a carbon neutral oil and gas industry, such as investment into direct CO2 capture to sign fuel technology, or essentially with the carbon reduction via oil and gas technologies?
Reappear. Yeah, I can answer that question. We can't speak to what the government will or won't do. We offer advice, and they choose whether or not to take that. So we'll deliver our final advice on the 31st of May, which is terrifyingly 6.5 weeks from now. And then from there, the government has to choose whether or not to accept the budget numbers that we recommend, and then also the direction of policy that we suggest in the emissions reduction plan. They then publish an emissions reduction plan by the 31st of December. And in that, they'll set out the policies that they think will deliver on the emissions budgets that they've set. So in terms of what happens with the oil and gas industry, I would look to what the government says in that emissions reduction plan. I think our report has said that we see a role for removals, and we put some suggestions in there around things. I mean, we did put evidence in there around the CCS potential and also the potential for BECCS and things that could help move us into net negative as well. Although those are probably not for the first emissions budget. I can't really comment on that in detail, if that makes sense.
Okay, thank you very much for that. And we will move on to our next presenter for the evening, Greg Skelton from Wellington Electricity. Greg is the Chief Executive, and he's here tonight to continue to talk to the theme of decarbonisation and resiliency through the grid, including in peak demand conditions. Thank you, Greg.
Thanks. Tanako, everybody. My name is Greg Skelton, as Hugh's just introduced me, and I look after Wellington Electricity, which is your local lines company, and I'm pleased to say tonight the lights are still on, so that's always a good start for me. What keeps me awake at night? It's really, hey tangata, hey tangata, hey tangata. It's people, it's people, it's people. So most of our role is really looking after the teams that work around our network, and it's around continually supporting a safety culture which aligns staff work processes and activities with critical risk controls. It's a bit of a mouthful. Or if you look at it another way, you're probably most vulnerable when you feel the safest. It's probably something you've forgotten. Anyway, what I'm here to talk about tonight is, as a lines company, we've been looking at what customers are starting to do around decentralisation, what there is value for customers in decarbonisation. And what's happening around moves in the computer age, cloud computing and digitalization that's going to help us start to manage some of these constraints which could be occurring in the future. And the final thing, the trick of all of this is it's a lovely crowd in this evening of engineering people, which is great, but we really need to reach the customers and make it understandable and believable for them. When we look at our supply industry, it's really an interconnected coordinated system. So we really have central generation which flows through a transmission system. Then it meets 29 lines businesses, the poles and wires around the roads and streets of our neighbourhoods. We have retailers who serve their energy to customers, and then we have the end consumer. So it's pretty much a top-down single power flow process. But the interesting part about where that's heading to now is all the really interesting stuff, all the cool stuff is happening at the consumer residences, whether it's be through solar panels or battery storage or the change across to electrification of transport fleets. And that's what I really want to talk to today. The thing about this is we have ways of managing how we interact with the power system and with our bigger colleagues at Transpower and how we manage those assets and their recovery. There's even a market regulation around how the retailer and wholesale generation works along with the infrastructure assets. But the thing we really need to move on to around this model of decarbonisation is thinking about the bigger picture of how industries and the consumers collaborate with the choices they're making. Storing energy at night is pretty much old hat. We used to do this back in the 60s and right through to the 90s when Richard was in short pants, really to keep the thermal power plants running. This is largely to have some base load overnight through night still heating or electric hot water storage that allow those to run through. So it's a real traditional thing to do. And we built a whole lot of very sort of basic systems around ripple control that could turn signals of these devices on and off, usually around 11 at night to start storing cold water into hot water and then turning it off at 7 o'clock in the morning for us to have showers and get ready for work. So when you see that bottom left picture, you'll see that the night still heater is really just starting to be replaced by an electric vehicle. So we're thinking about storage in that way, that we have systems that are actually have been built, and there's a lot of room in the night period to fill it up with some of that electric vehicles charging. We've done a wee bit of work since about 2017 where we picked 100 EV users in Wellington and started talking to them about what would be a price signal that they could live with, and also engaging with the retailers on our network, and there's about 27 of those, as to what would be the clearest thing to do for EV owners to make sure they charged outside the peak congestion period or when the network's the most busy, which is really about now till about 9 o'clock tonight. And we came up with a simple two-peak process, higher cost in the peak and a lower cost when it's non-peak. So a standard rate that used to be before this one, the time of use rate, the standard rate used to be sitting around 7 cents. And the rate we've got in now for electric vehicle and battery storage has a peak around 11 cents, which is much higher, and obviously a much lower 2.5 cents in the off-peak period. So that really gives people the incentive to save a lot of money by charging the vehicle at night. We also brought that through into people also able to do anything in their household to actually affect when their appliances run. Some of the advantages to consumers around electric vehicles is, although they'll use more electricity, it's really the removal of petrol and the price of petrol fuel in their household that's really the big saving. And that's really going to give most consumers, if they aren't running around with petrol vehicles and they've made the transition across to electric, around a 45% saving in their household energy costs per year. That's substantial and that's significant. And that does help to think about the life cycle cost of moving across to an electric vehicle, which in the front on the sticker on the window looks expensive. But when you start to drive around at 30 cents or with night charging 15 cents per the petrol equivalent of $2, it really does start to stack up. So there is some room there for entrepreneurs to start to think about how we decouple the purchase price up front and the life cycle operating cost of what it costs to operate. The thing about running an electricity network is we spend a lot of time looking at our high voltage network, 11,000 volts and above. We run about 55,000 points in real time under management through our SCADA system. That keeps 14 people busy 24/7. The downside is we don't do much on a low voltage network, mainly because there's 170,000 connections, and if we took 10 data points from those, it's 1.7 million data points. A bit busy for us to do much with. Therefore, the visibility of what would happen on our low voltage networks is outside our reach at the moment. So we've been looking at products that we can put into devices that gives us visibility of electric vehicles when they charge, and also over time some controllability. So we've started these processes in the last year or two, and what we're really doing is looking at taking that graph where that red peak is occurring and then trying to shift that down into the night period. We're trying to do that in a service model approach. Letting the customers of electric vehicles plug the vehicle in and then let the services run of actually how we can push that vehicle into its charging in the night period rather than when you get home. Plug it in when you get home at 5:30, no problem at all, and may not dispatch and be charged until later on that evening. Sure, you'll have the optionality of actually doing something different if you have to, but just think about that higher price you'll be paying for that optionality. We then moved it on a wee bit further and thought about working with some of our Australian technology companies, and they talked about bringing some of this investment that customers are making behind the meter visible not to just lines companies. So it's visible across the whole supply sector, and that really set up the concept of a distributed energy exchange, or a DEX system. And what happens with the DEX system is it allows the visibility of some of these appliances, the solar panels, the battery storage, the electric vehicles, to be seen by the whole electricity market. And that allows people to start to think about that. It allows customers some optionality of how to actually manage that through. There's a lot of paths to this. I'll skip through this very quickly. What it really means is you've got APIs starting to integrate smart technology, and then you've got some rules around making sure there's grid compliance. So that's making sure things stay in balance. It then moves into extracting the value from the customer of bidding in their solar or bidding in their battery storage for the wholesale market for frequency keeping, or they can really turn their house into a virtual power plant and bid into the market. It's a lot of work. We won't spend too much time on that slide. So therefore, if you've got devices that can be seen on a distributed energy exchange, and you've got consumers that have got those devices, and you've got alliance companies with a flexibility agreement, we can start to shift that around. But what it really means is the customers and their retailers start to get value of actually shifting their power plants around at times of getting the most value for the customer. It also means that the transmission grid operator has an optionality of shifting that load if there's constraints on that system. So in summary, we could build a bigger network and put our prices up. That's probably not going to be very popular as the price of all the things that customers buy come down. We could use a cost-reflective tariff, but that's only one signal. It doesn't mean to say it's going to keep the lights on if people still want to turn their cars on when they get home. We've also got the cost-reflective tariff and the water heater system, but that does not unlock load for everybody across the supply chain. So really what we're trying to head towards is the management and incentive payments to allow greater access to the devices that the customers are putting into their homes to allow us to actually manage our network a lot better. But the big issue for us is getting this message across to customers. And if I sat here and delivered this to a customer or my grandmother, she'll be sitting there and her eyes will be glazed over. So as engineers, you will understand this, and I'll look forward to your answers to the test at the end of the evening. But what we really want to do is put something in front of customers. So we've come up with this animation. I'll let you watch that, and that's the conclusion of my presentation. Just have to rewind.
At Wellington Electricity, we manage the power lines that supply electricity to the community. We need to ensure our network is safe, secure and sustainable to cope with everything you demand of it. Fast forward to the future and there will be more electric vehicles on the road. This is great for the environment, but the charging of these vehicles puts more load on our power lines. During the summer months, this extra load will be okay. But when winter comes along, we may have a problem. So, we need to work together to help us all stay connected and to keep the lights on. We could build a bigger lines network, but more infrastructure investment means we would need to charge you more money. Or we could manage how and when we charge our cars to lighten the load on the lines. Let's take a look at this. During a 24-hour period, we have peak and off-peak times. If we all try to charge our vehicles at evening peak times, the load on the lines is too great. If we instead charge our vehicles during off-peak time, there is plenty of power for everyone and it costs you less as well. We have worked out that together we can achieve a more sustainable and affordable system. All you need to do is use your car's timer to charge your car during off-peak periods. We'll let you know when these periods are, so you can sleep easy while your car charges. Or we can look after the charging of your car for you through a smart charger agreement, avoiding overloads and annoying power cuts for you and everyone in your street. So, if we all work together, we can save together and deliver a better renewable future for our community and the generations to come.
Okay, thank you, Greg, for your presentation and for the video illustrating what you talked about. We do have one question for you that we will just quickly ask you, and it's going to the point of the benefit of what is the benefit of having New Zealand split into distribution regions that are governed by discrete companies with their own standards and connection requirements.
That's a great question. I thank my retailer friends for asking that. Yeah, so there is a tradition of lines companies being set up into 29 different regions. And I suppose the idea of why we're putting these things up is it really follows our National Association's network transition roadmap, which is really starting to get everyone onto the same page and doing the same things that we're floating. So we've got also companies in Dunedin, Aurora Energy, who are doing very similar things at the solar storage end and looking at that as optionality for actually limiting how much investment they need to make on their transmission network into Wanaka. So those things are starting to come through as well. I suppose the same question really comes across most of the utilities that you see delivering service to your homes today. Water's another one. There's a whole series of councils as well. So you're right. The question is focused on with scale, you do get greater efficiency. So who knows? We might be one national lines company in the future. See what happens.
Okay, thanks, Greg. Next up, we have Liz Yeaman. Hello, Liz. Come up onto the stage. So Liz is the managing director of Retnia, and she was formerly the manager at ECA, and she led the electric vehicle program there. Now and tonight, she's going to talk to us about her work with electrification of a ferry service. Thank you, Liz.
Thank you very much. Hi, and good evening, everyone. I'm here to talk about a project that I'm really pleased to be involved with, which is New Zealand and, in fact, the Southern Hemisphere's first electric ferry that's being built here in Wellington, and it's due to be in the water, we hope, next month. To give you an idea about how close we are to getting it into the water, the last time I visited the ferry, the bar fridge was going in. So this is a little map that shows electric vehicle activity worldwide, and it's focused around the Scandinavian countries. They have really been pioneering in this area, but New Zealand is the only place in the Southern Hemisphere that's moving. Us and the Inter-Islander ferries, who are looking at hybrids, both have projects, not just, we're pretty close to going in, theirs is a little further away. So those of you who might not know East by West Ferries, they're a public transport ferry operator in Wellington. They've been going for over 30 years, and over that time have carried 5 million passengers. About half of commuters travelling into Wellington from Eastbourne on the other side of the Wellington Harbour, and about half tourism, and we're part of the Metlink public transport network. East by West currently have 2 diesel catamaran ferries that operate about 17 knots at the top speed, carrying just under 100 passengers each. And Jeremy Ward, the managing director of East by West, was needing to replace one of his ferries, and he started looking about 5 to 7 years ago at what would replace, and he really didn't want to buy another diesel ferry because he could see that in 10, 20 years, nobody would want a diesel ferry. He had a look around the world, and this was one of the inspirations for him. This is a ferry in the Norwegian Fjords called the Legacy of the Fjords. It carries 400 passengers at about 16 knots through a World Heritage area, and was one of the first biggest electric passenger ferries in the world. He travelled on that, not there at the time, but sitting in front of it is now what's called their power dock. So that ferry has 2 megawatt hours of batteries on it powering. The power dock that sits in front of it is a floating array of 2.5 megawatts of batteries. And what happens is, for the lines company's point of view, that charges continually and slowly all the time, so that when the ferry pulls in at a rate of 1.2 megawatts, that power is transferred to the ferry in 20 minutes. So it's quite a phenomenal thing that refuels that ferry and lets it go on its next journey again. So there's a combination, really innovative technologies there, the ferry electrification and this floating power dock that lets these ferries rapidly charge up without having huge pull on the lines companies. So we put together so Jeremy couldn't find anything internationally, and then had a look around, and we got together a group that's actually building that here. So New Zealand companies, Wellington Electric Boat Building Company formed to build this first ferry. The operator has actually been part of the design process, so we actually find out what the operators and skippers and crew need on the ferry. Mackay, who are based in Whangarei, do the electrical engineering. They also do the electrical engineering for the New Zealand Navy. SSC Marine and marine architects and designers that have designed the vessel itself. Really high energy efficiency vessel. It's being made out of carbon fiber so that it's lightweight, which is really important. You cannot, with battery technology at the moment, do this project without having a super lightweight, super energy efficient vessel. Gurit are the advanced carbon fiber composite company that's involved. They provided the composites for the America's Cup yachts. And I help a little bit around all the other stuff that nobody else wants to do. So the ferry is designed to be lightweight as possible. That's the only way that we can do a return trip with today's battery technology, is by getting that ferry super efficient in the hull form and as lightweight as possible through carbon composites. So it's designed and tailored to operate on that route. All the other ferries, they don't go anywhere else. They just operate that route, so we can really tailor it for the route. It's got an intelligent battery management system that optimizes the range and the battery life. 2 independent battery stacks, one in each hull of the catamaran. So if for any reason we lose one, we've still got the other one that can keep going. It's built to DNV class rules, which is a bit like Lloyd's Register. They have got standards for commercial electric vessels to ensure safety, multiple layers of redundancy, when anything that can go wrong, layers and layers right down through to all the batteries being in a 1 hour fire boundary, so that if the worst happens, we can still get everybody safely back to Wellington, and super high energy efficiency, as we described before. The battery charging cycle has been designed such that when it's in full operation, the ferry will come in and completely recharge for the next journey in the time that the passengers load and unload in 15 to 20 minutes. The ferry can operate at 20 knots, which is quite high speed, and the energy demand as you increase goes up exponentially almost with speed, so that if for any reason we found we were starting to run out of power, all you have to do is drop the speed of the vessel. That vessel can operate all day at a much lower speed. It's only at the high speed that it has that big power draw. So running out of power while you're out on the ferry is not something that we are anticipating being a problem, because of the multiple layers of care that we can take for that, and the fact that we've got the batteries in 2 hulls, and we just drop the speed and the power demand goes significantly down. There have been, one of the areas I've focused on is the charging infrastructure, and there are some particular challenges around that. East by West just has a tiny little ticket office on the wharf side. It's a pedestrianised area full of restaurants that pay for waterfront visibility and capacity. They don't want container loads of batteries and container loads of power electronics sitting around on that wharf. Very high pedestrian counts. We don't want stuff getting in the way. And the ferry also pulls in right at the bottom of one of the only view shafts through to Lambton Quay. So again, we don't want that blocked with stuff. And it's a heritage area. So quite a lot of challenges around that. The technology is also changing really rapidly. We looked at a lot of the Norwegian solutions, which are all very much custom built one-offs for big, heavy ferries. There is, however, a new standard coming from the people that have produced the CCS charging standard for cars. It's called the Mega Charging Standard. It was due out this year, but has been delayed due to COVID. It's a new global standard of a standardized plug and communications protocol that allows for charging of bigger electric transportation, such as buses, trucks, ferries, and short-haul aircraft. It's been put together by all of the major kind of trucking companies, even Tesla's in there going to be doing this standard, and the charging providers. There you can see it's a handheld plug. There's testing one of the models for it there. The guy is only wearing a face mask and goggles because of COVID, not because of charging. We came up with a staged charging plan. So we are actually, the most important thing for us is to get the ferry into the water and show it working. It is the first of its type in the Southern Hemisphere, and we have had some challenges along the way, not only from COVID and shipping delays. So it has cost us quite a bit more than we originally anticipated to do that. So our plan is currently to start off charging with an automotive charger off the shelf, 300 kilowatts charger. So it's the latest of the ultra-fast chargers. And we managed to identify some existing capacity on a switchboard in which we could do that. That means we can go fairly fast in order to get things moving. Once we've got the ferry operating in the water, we'll actually have some income from that, which means we can fund stage 2 of the charging infrastructure. And by then, the new technology we hope will be available, and that will go in as a phase 2. So that's the charger that will be going down on the wharf in the next month or so, and it plugs into a couple of sockets that are already sitting waiting for it on the side of the ferry that's there. We are also looking at, to make the most of that charging infrastructure that's going in, rather than just one ferry, is to look at a new ferry service to Miramar Peninsula with an onward literal last mile shuttle bus to the airport. This could see 2 ferries, electric ferries, operating every 50 minutes from Miramar Wharf. It would take from the existing ferry terminal to a refurbished Miramar Wharf 7 minutes. That compares with about 40 minutes at peak time to get around to Miramar. We think it will be a popular service, particularly for Miramar commuters, and we are trying to progress this concept at the moment. We think it's going to be a really popular service. So last of all, thank you to Greater Wellington for support through the public transport funding, and to NZTA that contributes to that, to Callaghan Innovation that's helped us with the research and development, and Dika, who has done a little bit for the demonstration technology as well. Thank you very much.
Thank you, Liz, for your insights there. Having lived in Norway sort of a decade ago and keeping in touch with their progress, I know that they are a leader with EV and ferries and vehicles in the Northern Hemisphere. And so it's very exciting to hear that New Zealand is rapidly becoming the leader in the Southern Hemisphere. We do have one question for you, and it's about alternative to electrical supply. Was hydrogen considered? Potentially this could be considering as an alternative to lines in remote location as well. So either hydrogen as a fuel source on the ferry or hydrogen to generate local electricity on the shore.
Yes, it was considered, but was ruled out because it was significantly higher cost. It is more expensive, but the hydrogen option would have been higher again. And also you have to look at how you would get that hydrogen to the wharf side when we've already got struggling to get something with a very, very small footprint there. If you had to have some hydrogen supply infrastructure, you have to have somewhere to put that down on that waterfront as well. And that takes up quite a lot of footprint. Thanks. Okay,
thank you, Liz. And following on from the mention of ECA on Liz's slides there, next we have Glenn Wellington and Kanchana Marasinga, my apologies. And they're from ECA, the Energy Efficiency and Conservation Authority, and they're here to talk to you about their work. Okay, thank you.
Cool. Kia ora, everybody. Thanks for the opportunity to talk. We're quite specifically here. Oh, who's got the clicker? there. Sorry. Come up. Right. Sorry, we got through it a bit. We're here more specifically to talk about one of the government funds, the Government Investment in Decarbonising Industry Fund. It's a bit of a tongue twister, so the GIDI Fund, and how that's helping New Zealand's large businesses accelerate transition to a low carbon future. There's very few upsides to COVID, but I think the delay in this event means we can actually talk about the round one projects and even potentially announce round two. So that's one upside. I'll give a bit of an overview of not so much ECA. Hopefully people do know ECA, quite a broad government agency covering residential, transport, product specs, but more specifically our area, business and public sector, decarbonisation and energy efficiency. Kanchana will talk about the GIDI Fund, and I'll just touch on the state sector decarbonisation fund at the end. Probably since about 2014, ECA has had a team of account managers working directly with large business, Fonterra, all the large dairy companies, Methanex, New Zealand Steel, right down to your sort of medium-sized councils. Really working hard to mobilise the decision makers to accelerate action and trying to catalyse projects, be it energy efficiency. Moved a long way from the beginnings of electricity efficiency, and carbon has become the focus, still within our mandate of energy. A lot of the work we do focuses on stationary energy and obviously process heat, but there's quite a active transport program that Liz has been well involved in, and that's building too. A lot of what we do is, we've got funding to co-invest, so catalyse those projects through our engagements, but then co-invest to help some of those barriers. A lot of it is sort of investigation, your traditional energy audits, feasibility studies. We fund energy graduates to go and work in some of these large businesses to really help on the ground to deliver projects. But more recently, and really setting the scene for the likes of the GIDI Fund, over the last couple of years, ECA have ramped up a new program called the Energy Transition Accelerator, where our account managers and actually right through all the senior levels are working with these large businesses to get the commitment to define a energy transition pathway or a decarbonisation pathway, 2050 in mind, but certainly really helping some of these large businesses set targets for 2030 and some real tangible outcomes. We co-fund work of consultancies to go in there and quite a technical initiative, technical analysis, pinch analysis, depending on the organisation, to really define technically feasible and as you're looking over longer periods of time, economically viable transition options and opportunities. Key thing to that is aligning it with asset replacement or even strategic growth initiatives of those businesses and picking the right timing. But obviously we're trying to accelerate that as well. ECA itself, we have a little bit of capital funding through technology demonstration, trying to bring in new technologies that aren't really up and running in New Zealand to help energy efficiency or decarbonisation. But laying out these pathways with it's nearly 40 odd now of New Zealand's largest businesses. One of the key barriers is capital, and how do we support that to accelerate it? Two funds have come along recently. State Sector Decarbonisation Fund announced in late 2019, targeting state sector organisations. I'll talk a bit more about that at the end. But the GIDI Fund really helping some of these large businesses accelerate projects.
Yeah, GIDI Fund has
Giddy.
Yeah, is it okay now? Yeah, that's fine. Yeah, GIDI Fund is government investment in decarbonisation industry. So the as Glenn said, it's 69 million capital for core investment, and it's established on the COVID recovery fund. So there are key aims for that. One is the decarbonization, and the focus is on the process heat side, and then the other main aim is the economic stimulus and domestic economy and supporting employment. So yeah, those two are the main themes for the fund, and the main principles for the funds are like the maximum impact. So how can we get the maximum carbon reduction through this fund, and also the maximum employment or economic stimulus in local regions or in New Zealand. So, and the focusing on that, and there are criteria or the trying to manage that, and we have said that the implementation readiness is key. So some of the options, and then the leveraging co-funding. So how far we can push. So that's co-investment is the key. So we fund part of it, and any organization that who will be implementing these projects support the other portion of the cost of the project. So, and we also want to encourage innovation, so bring in new technology or underutilized technology to New Zealand, and to utilize those technology and fund to mitigate some of the risk around those, and also the additionality. If it is anyway going to happen in 2 years, so we don't want to support that because it's anyway happen. So it is more about acceleration. So how can we accelerate projects that are in their pathway for 10 years later? And again, being eco, so we want to see the energy efficiency and demand reduction first. That's our principles, and then innovative technologies and also full switching. So ultimately the full switching once you do all these the process changes through new technologies or demand reduction. So yeah, so we just completed the round 1 of that, and we have invested 23 million in co-investment from this round, and about 14 projects announced. 14 projects announced. Average average tons per dollars per ton of investment is about 12.77 from the government portion. And we actually pleased about the project mix that we got through it. About 2 boiler conversion, 2 boiler replacement, new boilers, about 4 new boilers, biomass boilers, and 1 electrode boiler, 7 heat pumps. That could be about 16 heat pumps. And also most of the project had a demand reduction component attached to it. So, and all the businesses that are supported will have a carbon reduction pathway or will be committing to a carbon reduction pathway. And the second round is announced literally today and at 5 o'clock, so it's available now on our website. And for application, so it'll be closed on the 17th of May. And again, anyone who is applying will have to demonstrate the carbon reduction pathway. So to make sure that we are investing on the right project, so is that the right project? And it'll be kept at 50% co-funding maximum. So and also projects will need to be completed by the 31st October 2023. Again, it's a very consistent with the round 1. It will be a contestable process, and anyone encourage them to apply for that.
Yeah, so as Kanchana mentioned, it's all available on the website. There will be a supplier briefing as well, like we did with round 1. Can I just borrow that? Like we had with round 1. Like Kanchana mentioned, really good spread of projects, nationwide spread. Meat companies, dairy companies, Goodman Field and Napier Pines. So good mix of technologies, locations, and that co-investment, which is roughly 50% government to private sector investment, really driving some employment benefits in the economy as well. I will just quickly touch on the State Sector Decarbonisation Fund. It's been around a little bit longer. Again, doesn't include local government, but decarbonisation of government departments, DHBs, universities, a bit broader than just process heat too. So there are some transport, building fabric conversion, anything that results in carbon reduction, and obviously there's plenty of fuel switching projects in there as well. So message there, if you're working with public sector organisations and you've got projects on the go, get them to engage with ECA on potentially applying into that fund. I think of the 200 million, about 83 is announced. They're getting close to announcing the next round, which will get that about halfway through. So there's still some capacity there for funding projects. Cool. Thank you, everybody.
Thank you very much, Kanchana and Glenn, for your insights to your contestable funds. We do have one question here that was fairly generic and asked earlier on, but it's probably the right one to ask you. The challenge that, and I think this might be from a consultant, that they have is that their clients ask them for the cheaper option, not necessarily the sustainable option. So what would you say to that? Of course, bearing in mind the funds that you have, but also just in general to that challenge that's posed.
Yeah, it's a question about cheaper option today versus cheaper option in the future, and that's the consideration we all have to talk about, and that's why the ETA is quite important. We talk about the future as well, and it is again about the life cycle cost, and some of the analysis you might be doing now will be around 38 tons of ETS price or something. So it could change to $50 or $100. You don't know. So that's quite important. And also the things like you have to predict things like the signals. You have to read the signals as well. So someone who had invested on a coal boiler 2 years ago now might be thinking, have we done the right thing? So it could have been cheaper that now they're thinking about, okay, is it going to be fully depreciated by 2037? So it's all about all those factors. Yes, quantity and the dollars is important, as well as you have to think about the other important factors as well. So that's the message I think.
Okay, thank you very much. Now, so at this stage, I'll just do a quick time check with Greg to see how we're placed to move on to the next presenter. So we will be taking a very short break at this stage. So we have concluded the presentations in the Wellington room here. So we're now moving over to a series of online presentations. So bear with us for 2 to 3 minutes, just as we set those up, and then we'll move through. So take the time just to step away from your computers if you're online, or if you're in the room, to just go outside and mingle for a little bit, and we will be back very shortly.
Hi Matt, can you please turn on your mic and camera? I just want to see that you can come into the room and you can use everything.
Sure.
So I can see your camera's on. Do you just want to use your mic?
Yeah, can you hear me okay now? Oh, can you hear me?
I can hear you off my laptop. I just want to see if I can get the sound louder. Okay. Do you just want to talk for a bit?
Let's just start talking about hydrogen, get people excited.
Are you able to just go onto the arrow next to your mic and just see that the volume is on the highest? So you're on mute at the moment. There's no sound coming from.
Hear me now?
Yeah, okay, cool, we can hear you. So, Matt, do you just want to quickly flick through the slides and see that they're all there and that you're happy with that?
Sure. That one's a little bit out with the heading, but it's fine. Are you able to adjust them there or not?
No, we won't be able to adjust what's missing, sorry?
Oh, just the heading. That's the last word's carried on to the next line, unfortunately.
Okay, well, we won't make that change, but just be mindful of that when you are doing the presentation. So Christian's going to go first, and then you're up next, so you can turn your camera and mic off in between. Hugh will introduce you, so we'll just get you to turn your camera on when it happens, and then at the very end we'll do Q&A, so you'll have to have your camera back on, but keep your mic off unless a question's directed at you because of the fact that there might be some feedback.
Yep. Sorry, what was that? Keep the...
Sorry, there is a lot of people in the room. So when we do the Q&A at the end, with everyone on, your camera will be on. Turn your mic off unless the question's directed at you. It's just so that there's feedback. Okay, so I'll just ask that you turn your mic off and your camera off, and then we'll go to Christian's one, and we'll just wait a few minutes until everyone's back in the room.
Right.
Just for everyone in the virtual room, we're in the process of bringing people back in. We will be getting underway in a few minutes.
Okay, thank you everyone and welcome back. So we are ready to resume with our next series of presenters, all of whom will be presenting remotely. To start us off, we have Kristen Jensen, a project director from WSP, who will be talking to us about electrical buses and hydrolyzers. Kristen, I'll hand over to you.
Thank you. So many of you are wondering why electric buses and hydrolyzers. Well, the answer to all of this is that it doesn't matter which way you go. So a little bit of background to me. Who am I? I've spent 40 years in the heavy industry side of life. 20 years ago, we were putting 40 megawatts down mine shafts and electrifying at that time because of our restricted atmosphere. And when we came up to the surface, we wondered why everybody else hadn't electrified. But part of that, and what we'll be talking about today, the grid impacts, hydrogen versus batteries, how do you optimize the battery, and what have we done in Wellington, carrying on from where Liz was. So first of all, a few notes of acknowledgement. Thanks to Haringa for some of the infographics and some of the figures that we'll be talking about. And also just to give you an idea of the scale. So one of the projects WSP was involved in was the Ellen Ferry over in Denmark, and that currently draws between 11 and 13 megawatts when it's connected to the dock. Right, we're just restarting the camera again. Okay, so now let's start rolling. So, as I've said, whether you have a battery electric vehicle or a fuel cell vehicle, you need electricity in the process. Every fuel cell has to have a battery, and the hydrogen technology is moving along rapidly. So whilst you might buy an electric vehicle now, you might be looking at hydrogen in the future, but typically you might be looking at some specific niche areas where hydrogen might work well in one area, batteries work in other areas. So we'll look at that in a bit more detail later on, and I'm sure Heringa will offer some options on that. As Wellington Electricity mentioned, the entire distribution network remains one of the risk areas. You can see in the photographs here some of the infrastructure that we're putting in, and if you look in the bottom right hand side you can see all those ducts going in. All of those are having cables going into some chargers in a bus depot, and believe you me, you only want to dig up the bus depot once, so you've got to get it right the first time round. Behind this, there are a lot of aspects that are being affected. Market rules, dynamics, the tariffs, the energy retailers, who controls those resources, how much you're paying for the electricity, and what happens when the power goes off? How do you keep things going? So those are factors you have to consider. When you start looking at hydrogen, it has an advantage that you have quite a high specific energy density, but there's a lot of discussion around, well, what's the efficiency? So what you need to do is to have a look and see where the niche works and where the specific density is the crucial issue. So from my perspective, which is in the infrastructure, you need electricity. You need electricity to generate hydrogen. You need electricity to charge your batteries. They've both got an electric motor. They've both got batteries. The difference at the moment is I can buy an electric car. I'd go out and lease a hydrogen car. But I'm sure that's going to change quite rapidly as we go forward. So again, thanks to Heringa for this infographic, which just shows that the two can actually operate in parallel. You could have an electric grid, and you could, like we currently have a natural gas grid, you could introduce a hydrogen pipeline. Now, there are some tricky things to do with hydrogen that need to be considered. It's a very small molecule. You can get hydrogen embrittlement. Seals are a little bit more difficult. Leakage, that sort of thing, you've all got to deal with quite carefully. You can't just introduce 100% hydrogen into a natural gas pipeline. It doesn't work that way around. On the right-hand side, these are the two typical sort of buses that we're dealing with at the moment. So one of those is the inner city bus, and some of you who are running around Auckland may have been on the electric bus without even realizing it until you stood next to it. Very quiet. And then down below is the hydrogen bus, which is just starting its trials. So the question around the whole thing is, how do you decide how much energy is being demanded? Now, it doesn't matter whether you're charging the battery or charging the hydrolyzer to generate it. You've got to draw the power, and you have to look at when you draw it. So when you look at the use of that energy, you're looking at the vehicle itself. So we have a tool called BOLT, and that stands for Battery Optimization and Life Cycle Tool. And what that does is it looks at the physical characteristics of your bus or your truck, curb weight, frontal area, drag coefficient, coefficient of rolling resistance. And so it even considers what tires you're using, the pressure that you're running at, the road that you're running at. It then looks at the efficiencies of the powertrain, the battery sizes, weights, transmission, regenerative braking, the speed, looks at the output power, efficiency, and from all of that, we can then see this is what the vehicle requires. Then we look at the trips that are undertaken, where they stop, start, the topology, it raises in elevation or drops, passengers coming on or off, the route that's followed, where you have to pull in and out of traffic, is it revenue, non-revenue, how many passengers are getting on and off, do you have the air conditioning on, who's the driver, how heavy is his right foot, Does he want to get home in a hurry? Is he going for lunch? They all affect the energy demand. The other thing that affects not so much the energy but the peak demand is when you decide to charge this bus. And this goes back to what Wellington Electricity was saying. So here on the right-hand side, we have a graph showing very similar energy demand, slightly different scale, unfortunately, is that you could charge through the day while the routes are running, and you'd peak out at about 3 megawatts in this particular example. But if you put all of that on after 8 o'clock at night, you'd need something like 12 megawatts. So those are your inputs. Now what Bolt does is it has a look at all of the schedules, and we start sucking these in from all the fleets that are running, all the buses that are running, all the revenue trips, what's happening, and that gets pulled into a database. And what we found, and it doesn't matter whether we're looking in Jakarta or in Canberra or over in Brampton in Canada and here in Auckland, we can get down to an accuracy of about 4%. Now that's quite interesting because the driver himself can have an impact of 6 to 15% on the energy. So once you've got all of this information in place, you can start to make some decisions. And those decisions could be around the route that you're traveling on, how you're going to schedule it, how many buses you require, what type of bus you require, how frequent you're going to run those. And out of that, we generate graphs which show you this is the topology of the route, and the bus climbs up to about 80 meters above sea level and then starts running down the hill. And in the process, it's getting more passengers coming on. And so we actually gain a lot of regenerative braking. When you start putting this together with the air conditionings running, the number of passengers that are going on, we can actually see exactly how much power is required per route. And at the end of the day, the whole issue is how do we move this forward into a net zero economy? And that's part of the issue behind it, because we need to be able to generate this power. We need to be able to transmit the power. You need to be able to store it in the vehicle, whether that's hydrogen or batteries, and then you want to be able to use it. So here we have a couple of different types of chargers, and usually they're typically about 80 kilowatts, above 180, and that's now rising above 250 kilowatts. You're going to liquid cooled, and our whole models look at exactly how it charges, what happens with battery degradation, speed and timing. And here's the one in Wellington, down in Reef Street. That's a Helios 430 kVA charger that we put in with transit. Quite an interesting earthing scenario down there where we had children coming out of the local swimming pool, barefoot, wet, hugging the charger because it's nice and warm. So it's a charger in a public place, so you have to make it safe. You can see the scale of this bus, and you can also see the fact that the pantograph at the rear was, and this is quite cleverly done by Transit, because of clearance requirements, pantograph was moved to the rear to decrease the profile. So there are ways of doing things very well. You can see here this was on an original trial where we actually found that the clearances were a problem. Okay, so out of this you can see that you get different results out of Bolt. Here's two different chargers, one 80 kilowatt, 150 kilowatt. One doesn't give you room for growth, doesn't finish charging by 6 a.m. in the morning. This one does finish charging but has a higher peak, so you can make different choices. We've put out a couple of white papers on this if you want to read a little bit further, and you can see the whole interconnection between connected vehicles, autonomous vehicles, shared mobility. It all rolls into this. So I'd be quite happy to talk to people individually about this a bit further, and look forward to any questions later on at the end. So finally, in summary, you need to realize that you've got to talk to a lot more people. There's grid capacity, grid planning, depot planning, and urban planning. It all comes together. You need to talk to everybody, not just the people using the bus, not just the people running the bus, but the electricity companies, the transport authority, and town planning. I hope that's given you a bit of food for thought. Thank you.
Thank you very much, Christian. That was a round of applause from the room here in Wellington. We do have several questions, some pertaining to the generation of hydrogen, but I might leave that for our next presenter. Just out of interest, in terms of capacity, what do you see the challenge being in terms of rolling out more electric buses in New Zealand?
Much of it is around the interaction between the fleet owners and the electrical utilities. And I'll be honest with you, many of the bus fleet owners who I've worked with here, Australia, Canada, underestimate the magnitude and the impact of the energy demand. We have some bus depots over in the States which are going to be running more than 8 megawatts. We have a couple here in New Zealand which are going to go well beyond 3 megawatts. And all of a sudden the CFO gets a big fright when he sees that his energy cost now becomes his single biggest cost. So it's a cultural change. We find many of the diesel mechanics are very keen to learn these new skills, and it is a changing environment. It does require new skills, but they're available in the market.
Okay, thank you very much. And with that, we'll move on to our next presenter, who will be discussing the production of green hydrogen and uses in decarbonisation. So Matt Lucombe. Matt is from Herianga, and over to you.
Thank you. Tēnā koutou katoa. Hi, so a brief introduction to Herianga Energy. We're a green energy developer focused on building hydrogen refuelling infrastructure for New Zealand. To do that, we're also investing in renewable energy to feed the hydrogen production, building the refuelling stations, and a big part of the team is actually facilitating the market use of hydrogen. At the moment, there's no off-take on the heavy transport side, so we have to get the trucks in, get people who want to transfer the goods around on trucks and that sort of thing. So a big part of the team is actually the commercial side of things. So we're not a technology provider. We're really a commercialisation model, so focused on the right applications and the scale to build a commercial model for hydrogen heavy transport as well. I've got a few slides being engineering talk about hydrogen production, so just bear with me on the technical stuff. So most hydrogen at the moment is made through steam methane reforming of natural gas. Obviously that produces CO2 unless it's injected back into the ground or used. So the shift is towards green hydrogen, which is made using renewable energy and water. The process is electrolysis. Essentially, you split the water into hydrogen and oxygen. A large portion of the energy stays with the hydrogen and is carried that way in the gaseous form. And then in a fuel cell, the reaction is reversed and you get the electricity back and generate water again. And you have a cycle where effectively hydrogen and water carry your renewable energy and allow that to be used at a different time from when it's actually produced. The actual electrolysis itself, this is a PEM electrolyzer, or a proton exchange membrane. This is sort of a newer tech for producing hydrogen. Essentially, you have water and you put it across an electrode at the anode. The water is split into oxygen and protons and electrons. The electrons follow the electrical circuit, and the protons are small enough to fit through the membrane and flow through that, and then they reform on the other side of the electrolyzer, and you get hydrogen produced. The membrane effectively separates the hydrogen and the oxygen, so you don't have the two together with a thermal mixture. The key part to it is also having deionized water to feed the system, so it works well from that point of view. And the actual electrolyzer skits themselves, so the systems we're using typically come in a 40-foot container. The electrolyzer is quite a small piece, and there's a lot of balance of plant. We need to clean the water up to take out the ions. There's about a third of the energy ends up as heat during the process, so we've got to take that away with the cooling system. We have hydrogen and oxygen separators in the process. and a large electrical system to provide the DC current electrolyzer. And finally, we have a scrubber to take out any oxygen which carries through the process. So quite a lot of kit for probably about half of the cost is the electrolyzer and the rest is the balancer plant. The balancer plant is a pretty common kit which is seen through a lot of industry already, so it's quite an easy process to adapt for this sort of industry to take on. So now I'm going to talk a bit more about how you get hydrogen commercially. So as I said, Haringa is not about demonstrating hydrogen. There's about 550 hydrogen fueling stations in the world at the moment. So we're looking at finding commercial models and focusing on its best application. We think hydrogen is this is part of the solution. It's not a golden bullet, but it's got a nice niche place to play around industrial, chemicals, and heavy transport. We've kind of scoured New Zealand, looked at where's hydrogen going to be used, looking at forklifts, buses, and trucks, and seeing where's all the demand. To make the hydrogen, you need to have renewable energy. So where's the existing renewables? Where's the wind? Where's the geothermal? And hydro, and then also where's the new options for wind development and solar in New Zealand. And you couple it all together and you get a nice map around where are the best places to actually make hydrogen successful in New Zealand. So as I said, hydrogen is not a silver bullet. It's got some great applications. So to get a commercial outcome, we've looked at where can you get a high price for your product to help get it away, and where is the market size potential. So when you look at the energy sector, liquid fuels have a premium price of energy, typically an order of magnitude higher than gas fuels. So going to heavy transport and passenger cars make a lot of sense from that point of view to get the best value if you want to try and compete with the existing incumbent. Whereas gas, it's a lot lower price point on an energy basis. Then you look at where's hydrogen best suited. Passenger cars work well for most people. You can recharge them overnight and you get the efficiency benefits compared to a hydrogen system. Whereas heavy trucks are quite a logistical challenge for batteries. So that's why that works really well. The market for hydrogen heavy trucks is quite large. Also, the export market is a big market, but the price point's very low, and we see that as being a second and third sort of phase development. And the other one is the industrial feedstocks. In New Zealand, we've got 2 or 3 large users of hydrogen. They get it from natural gas at the moment. So they can provide the sort of scale you need to help get low-cost production and give you a bankable market to get a commercial product away. So let's talk a little bit about the applications. So heavy trucks and buses are the key ones for us. And it's been alluded to already that the hydrogen trucks are actually electric vehicles, but instead of carrying a large battery, they carry hydrogen because of its weight advantages. So a typical truck's going to carry around 50 kilograms of hydrogen, and that's going to give around 500 to 600 kilometres of range. And we'll have the same fueling times and applications as a diesel alternative. In the truck itself, it will consume the gaseous hydrogen. It's about stored at 350 bar, so similar to what the CNG systems were, and convert that in a fuel cell back to electricity and use a small battery to provide that surge lighting on the truck and then run the electric drivetrain through the truck. The key parts are the refueling times are very fast, so we're looking at between 10 and 15 minutes for the trucks, which is comparable to diesels, and you get the same advantages of an electric vehicle with torque and no noise and so forth. The other key space we're looking at is the industrial offtake, and that's because of the market there to get a bankable and financeable project. So in Kapuni, we've got a ammonia urea plant. It makes around a third of New Zealand's urea. It's the only urea plant in New Zealand, and it currently uses natural gas to make that. So in Kapuni as well, we have a fantastic wind resource, really well suited to the latest generation large wind turbines. So we've teamed up, so Haringa and Balance have teamed up to develop a project there. The key construct of the project is 24 megawatts of wind, so it's 4 or 6 megawatt turbines. And the way that the commercialities work is the first tranche of power, when the wind is blowing a small amount, goes to Balance to power their plant. And that provides a commercial offtake for power for the project. When the wind blows a bit more, we then take the power and put it through the electrolyzer. take that hydrogen and we feed it into the plant as a feedstock to make marginal urea. At the moment, the plant is constrained on hydrogen production, so we can make more urea without competing against natural gas. We're now competing against the price of imported urea. So we can get a comparable cost project which works from a urea point of view. We've also got options to divert the power to the grid. The electrolyzer can turn off in a fraction of a second, so we'll be able to have a virtual peaker there to support the grid. And when the wind's not blowing, we'll be able to take excess power at night when there's available excess renewables around it to make hydrogen and more urea. We can capture that energy which would have otherwise been spilled. And the big prize really is actually establishing the transport market. To make cheap hydrogen, you need to have low-cost energy, which we have through the direct connected wind resource, and you need scale. So 5 megawatts of electrolysis is big on a world scale. It means we're producing hydrogen at a lot lower cost than we'll be through the rest of our network. And it's a Bancorp project. The investors like it because we've got offtake. We're not building a large-scale hydrogen plant and waiting for the users of the trucks and the cars to come along. So it's a really logical place to actually kickstart hydrogen New Zealand. You couple the quality of the electricity resource and the wind and the offtake for hydrogen. That project will be coming online. We're just working through the consenting now. Hopefully this time next year we'll have the project online. So I know when most people talk about hydrogen, as engineers, we think about efficiency, and it's not as efficiency as electric batteries, and that's technically 100% correct. But when you're running a commercial model, electrical efficiency isn't the only efficiency to consider. And a lot of these things have actually been talked about already around the network capability. What hydrogen does, it decouples when you produce your energy from when you put it in a vehicle. So at night time and off-peak times, you can actually take renewable energy and store it. So you're paying less for your energy than you would be for putting it in a battery, and your grid doesn't need to be upgraded. So we can take those off-peak periods as well. Not only that, we can justify investment in renewable energy because we can load follow it. So as far as from a network point of view, both at a generation point of view and a transmission and distribution system, hydrogen is actually a really effective way to utilise the existing assets. The other part of efficiency, one of the other parts is payload. We're talking 50 kilograms of hydrogen versus 7 or 8 ton of battery in a truck. That's about a quarter of your payload is lost by hauling batteries around. So that, you either look at 2 trucks to do the job, or you've got a lot of stopping and charging to do it. From a time point of view, as I said, hydrogen trucks can recharge in 10 minutes versus if you want to put a megawatt into a truck, you either need superchargers doing sort of 4 megawatts, or you need to take several hours to charge them at sort of 500 kilowatts. So either way, you've got a trade-off of charging time and weight to make it work. And finally, another key one, which is the big focus around converting electric cars. And a key part to think of is actually the cost of the vehicle transition. So these trucks at the moment are about twice the cost of a diesel truck, and these are some of the first trucks being built in the world. With scale, they'll within 3 or 4 years be at a comparable price point. But when you look at the CO2 emissions from those trucks, so one truck is equivalent to 150 cars. So one fuel cell truck costs something like $700,000. If you were to buy 150 electric cars, it costs us around $9 million. And that's not buying Teslas, that's buying, Kias and those sort of things. So from a cost of transitioning your vehicle fleet, it's an absolute no-brainer as far as low-hanging fruit. And not only that, a lot of people can't afford brand new electric cars as well, and so the burden can move more to industry and those sort of places. And you're hitting the scale, which is why the costs are going. The big trucks are doing 300,000 Ks. They're 15, 20 times heavier than a car, so it's no wonder that it's more efficient to put your resource into transitioning those vehicles. And these are just some slides to really sort of emphasise, all this has been covered in the other discussions around the impact of trying to do battery versus fuel cell trucks. Your fuel cell trucks will require you to have massive loads when they charge during the middle of the day. Because of the sheer amount of power they use and the weight of the batteries means that you need to charge them often during the day, and you end up hitting the high cost points and the peaks of the grid. Hydrogen decouples that when you produce your fuel. And as I said, the heavy trucks are the low-hanging fruit as far as their emissions go. Like 4% of the vehicles in New Zealand are heavy trucks, but they're over a quarter of the emissions. So it's a great place to start and really utilise our renewable energy to that where we can best for our carbon reductions. In particular, the line haul trucks. There's a small portion of the trucks every year which are doing a lot of the Ks. I think the average truck does around 25,000, but the line haul ones often do over 200,000 or 300,000 Ks. So those are the trucks which we should be going after. The other ones doing a disproportionate amount of emissions. This is a case study just to kind of highlight how, why the electrical efficiency isn't the be-all and end-all as far as the commercialisation of heavy transport. So these are the trucks you can buy right now. The fuel cell truck, which we bring in from Hyzon, you can generate enough revenue when you recover your hydrogen costs and your ownership to make a good profit on it because of you're not refueling, and you can buy hydrogen and make the electricity at the points when you're off peak market prices. The current available comparable, or as comparable as you can get for heavy transport, for battery systems, when you look at their range and the lost time for recharging, and you actually factor in the cost of that, they can't make the economics work. So this is our case study of how it all works. And just a final wrap up on our network. As I said, there are around 550 filling stations in the world. Most of them have built stations and waited for the cars to come. New Zealand is so well positioned. We can have 4 stations in the North Island and cover the main freight routes and have a network which is viable for operators. So we can have a small amount of trucks filling up the stations and making them viable. It means that we can get hydrogen at a price point which is going to make the cost of hauling freight around New Zealand comparable to diesel in the short term. And it's my last slide.
Okay, hi everyone. I'm John Worth. I run a business called Geo40, and we have a pretty simple mandate. A sustainable future relies upon sustainable minerals, and you would have heard plenty this evening about lithium. Silica is a mineral I'll talk about. It's the future of natural nanotech, and cesium is the foundation of 5G and GPS and timekeeping. So all of these minerals can be found in geothermal fluid, and I guess Geo40 is a company that was formed at the intersection of, I guess, geothermal energy and minerals, and our mandate is actually incredibly simple. We will use genuine kaitahitanga and kaitiakitanga to recover minerals from geothermal fluid. And over the last 7 years, we've worked with the Ngāti Tahu Tribal Lands Trust and with Contact Energy, I guess, on a journey to recover, sustainably recover minerals. And in lots of ways, this is just a really simple story of leverage. What I mean by leverage is in 1958, Contact Energy, the New Zealand government commissioned the Wairakei geothermal power station, which Contact runs today. And that was the world's first large-scale flash steam turbine plant in the world. And here we are, I guess, roughly 60 years later with the Provincial Growth Fund, I guess the government again supporting what we would consider to be the next round of geothermal innovation. So that's the story I'm going to tell you today. I realise it's the last presentation, so everyone's falling asleep. So I'll do my best to keep you awake. I guess first things first. This is very much geothermal is very much a global opportunity. This is the I guess the ring of fire, the tectonic plate boundaries. Anywhere where you see red, you will find lots of Kiwi engineers working in the geothermal space. Whether we're talking to people in Indonesia, Turkey, or the Eden project in Cornwall, you will find New Zealand geothermal expertise working across the sector. And I think that's, to a large extent, that's what we mean by leverage. When Geo40 first set up, we didn't want to do something that was, in a tech space, a completely greenfield thing. We wanted somewhere, or an industry, where we could get leverage from that existing expertise. So in our case, we get leverage from the geothermal assets that exist in New Zealand. We get leverage out of the expertise and horsepower, intellectual horsepower that exists around geothermal. I guess just moving along, it's time for a very quick lesson in geothermal minerals. The mineral content of geothermal fluid varies quite a lot around the world, and actually even from field to field. But the one mineral that is ubiquitous is silica, and I'll talk about silica some more. And silica is important as a nanoparticle, very, very small particle, because a lot of the other minerals in geothermal fluid hide behind that silica. So if you want to get lithium out of geothermal fluid, one must first deal with the silica. And I guess this should not have been a surprise. For anybody who knows their history, this is an old oil painting of the pink and white terraces that were destroyed by the 1886 Tarawera eruption. And this is effectively the phenomenon of geothermal fluid saturated in silica, cascading down a hillside, and what is being deposited on those terraces is silica. And so the silica is being deposited as the fluid cools, and so that is exactly what we have set out to replicate in a mechanical way. And I'll tell you a dreadful story. Geo40, one of the first things we do in our plant is quickly cool the fluid to 40 degrees, hence the 40 in Geo40. There's another dreadful story which the engineers will appreciate, which is that the angle between the two hydrogen atoms in a water molecule, and Geo40 is a company that effectively processes water, is 104 degrees Fahrenheit. 104 degrees Fahrenheit is 40 degrees C. Not a explanation for the investors, but a good one for the engineers. And so we are a big believer in, I guess, the moving from the lab to pilot scale and then growing from pilot scale. So this is one of two pilot plants that we deployed almost 5 years ago now. This one is actually, in this photograph, is sitting in Japan and was very successful in recovering silica from geothermal fluid in Japan. So this is, 3 40-foot shipping containers. Our team can assemble this on a site and get it running in about 2.5 days. This plant, and we have another one of these plants in New Zealand, and the New Zealand plant toured the central North Island across a number of the geothermal sites, and again proved that we could recover silica from geothermal fluid. So these plants do about 100,000 litres a day in terms of fluid processing, and they're a great, a great proof of concept. One of the things about scaling up, and one thing that you'll hear us say consistently is scaling at an appropriate level is one of the most important things you can do in the mechanical space. And so from here, we built our first fixed installation. This is what we call our NAFA plant. It operates on a dead-end branch line at the Ohaki geothermal field. So this is roughly $3.5 million asset, processes 800 tonnes per day of geothermal fluid, so roughly 8 times the size of the pilot plant. And this plant was important for us because it produced our first sellable product. So this makes about 500 tonnes a year of colloidal silica, and that's being sold to customers all over the planet, from Japan to the States to Mexico to you name it. And having run this plant for the best part of 3 years, that gave us the confidence to go out and raise capital and build a proper plant, a big plant. So this is the one we've just commissioned. It's been running for, find the cursor, it's been running for 9 weeks now. We call this the Northern plant. It'll do 5,000 to 8,000 tonnes of high quality colloidal silica per year, and it is genuinely the world's first silica recovery plant from geothermal fluid in the world, which is exciting, and we're super pleased to have brought this to a close. So this has been built with the substantial support of the Provincial Growth Fund and a number of investors. And I think the thing that's interesting about silica is, I guess, two things. It's both a problem and an opportunity. It's an opportunity in the sense that it's a valuable industrial ingredient, and I'll tell you a little bit about what we do with silica in a moment. But it's also an enormous problem for the geothermal operators because of what we call silica scaling. So this is a 5-year-old re-injection pipe. The outside is the steel, and that's silica building up on those pipes. So independent work would suggest that about 25% of the operating cost of a geothermal power plant is dealing with silica scaling in the re-injection pipes and the re-injection wells. So these are $10 to $12 million re-injection wells. Rather than lasting the 20 years that they should last, they typically will last 4 or 5 years before they're blocked with silica and have to be rehabilitated or replaced. Now, as I mentioned, silica is also something of a gateway drug. If you can get silica out of geothermal fluid, you can do a number of interesting things. You can utilize some of the heat in the geothermal fluid that was previously unutilized. So we're typically working with re-injection fluids at 140, 150 degrees C, and in some cases around the world up to 200 degrees C, because of that, the silica in the fluid. Once we've taken that out, the fluid can be re-injected at potentially 70, 80 degrees C, and you can couple a binary plant, something like a climb-on plant, or another technology on the back end and generate some more energy. You can sell that heat to heavy industry. And once you've actually done something with the heat and taken the silica out, you can then sequester around about 2/3 of the CO2 emissions at a geothermal power station. So you would have heard the Climate Change Commission roughly a month ago make some very strident comments about a number of geothermal power stations that should close by 2030 because of their geothermal emissions. We're working very hard to, I guess, be an enabling technology to deal with those CO2 emissions. And I guess now, just on silica, what is silica? Quick lesson in, I guess, nanotechnology or natural nanotechnology. We are effectively making a silica dioxide particle, very, very small, about 8 billionths of a metre in diameter. And what that means is it's got incredibly high surface area. So a matchbox size quantity of colloidal silica has a surface area sufficient to cover a rugby field. If you take a 20 kilo bucket of colloidal silica, that will cover, in a surface area sense, the area of an America's Cup racecourse. And what that means is silica has very interesting mechanical properties. So we sell it, and have been doing for some time, to Resine, probably the most sustainable paint company on the planet, and they use it to reduce the quantity of titanium dioxide in paint by improving the molecular spacing of that titanium dioxide. So I guess we have two niches in silica. We displace conventionally made colloidal silica. So the normal route to make colloidal silica is to melt quartz sand in a blast furnace, then via an intermediate product, and then solvent extract to colloidal silica. That has a pretty outrageous carbon footprint. For every kg of colloidal silica, the CO2 footprint is about 2 kgs. We're currently working through our own carbon footprint, but it looks like for every kg of our colloidal silica, we're about 0.1 kgs of colloidal silica, 0.1 kgs of CO2. And so that's quite exciting. We've got a number of customers around the world who are switching to our colloidal silica. They include people using silica as a downhole oil catalyst as part of a decarbonisation strategy to avoid drilling new wells, and they're choosing our colloidal silica over incumbent colloidal silicas. And so those displacement markets are exciting. But for us, we see a much bigger future where we're using our natural silica nanotech to displace things that are having a deleterious effect in the environment. So we're very active in sediment and dust control. The predominant products used for sediment control are polymers, PVAs and the like. They end up as microplastics in waterways. If you want to do dust control, the only real options are refined oil or highly corrosive magnesium chloride. We make a formulation that's more effective, and of course, what does it break down to? Exactly what it was to start with, silica out of the earth, amorphous colloidal silica. One of the niches that we're particularly excited about, and I love this picture, little known fact, the manufacture of cement globally accounts for 8% of CO2 emissions globally. It's absolutely enormous. Colloidal silica has an incredibly effective role to play in the cementitious space. We have been selling colloidal silica to a number of the large admixture suppliers for quite some time. A lot of concrete admixtures are colloidal silica and plasticizers. We are very motivated by the direct use of colloidal silica in ready-mix concrete. What we know we can do is achieve better cement efficiency, better workability, and better durability. So we can, with very, very low rates of colloidal silica, can make a huge impact on concrete durability. We can obviously deal with workability, and we can also result in cement efficiency being greater and being able to drop 10 to 20% of the cement content in concrete, which is commercially compelling and has a direct and linear reduction in the CO2 footprint of cement, which is exciting. And then I think, for us, our hypothesis has always been that of a multi-mineral company. You've heard me talk about silica. I guess it's the enabling technology. We have interests in a few other places. We have started some research in the US, co-funded by the Department of Energy in the US, into cesium and antimony recovery, so down the left-hand side of the periodic table. That is, I guess, entering the stack for us. It's a different process. They're all different processes for different minerals, and I'll tell you a little bit about how we target these minerals. But just back to the chemistry lesson, top left-hand corner of the periodic table, the one that has us particularly excited and probably has the world particularly excited is lithium. And we've been busy on lithium for a couple of years now. We've had a test rig running 24/7, 4 days a week, successfully recovering lithium from geothermal fluid in the central North Island. And I guess the obvious question for us is what's next on lithium? That is our lithium rig that ran 24/7 for a period of time. What's next? Probably doesn't take a rocket scientist for you to figure out that it's one of these. We are heading towards the design, build and deployment of some pilot plants that we can deploy both in New Zealand and offshore. In the lab now we've processed brines off 3 continents, and it doesn't take a rocket scientist to figure out where the global lithium brines are that are most interesting. And we are not too far off, I guess, off some media around embarking on a very ambitious program to move ahead with lithium recovery in the field. And I'll wrap up in a second because I know everyone's tired, but we are, I guess, working our way towards becoming a serious company. We're not too far off cash positivity out of $25 million worth of assets in the field in terms of income producing assets. We're roughly a $65 million business now. And look, I think the message for me is that, or a couple of messages, we are an assemblage of diverse engineering skill sets. I'm a civil engineer, spent a long time in the renewables business, or structural engineer, which of course is useful around concrete. We have some remarkable process engineers, chemical engineers, mechanical engineers, chemists. That overlap between chemists and chemical engineers is important to us. And the really important stuff happens in those interfaces. in bringing those disciplines together around a vast volume of very strong coffee. That's what allows us to develop innovative world-first processes around mineral recovery. And we delivered, over the last 48 hours, we delivered some technical work to some of our partners in the lithium space, where we are now achieving lithium recoveries in the high 90%, which is in the lithium space is unheard of. So we're super excited about the future. We are, I guess, we're here as a function of an evolving New Zealand tech, I guess, ecosystem. We've got some incredible investors, the likes of K1W1, Pacific Channel, Hans Albrecht, new to the scene, EFU, and we have had incredible support from NZTE, the Provincial Development Unit, who helped fund our northern plant, and of course contacted the Ngāti Tahu Tribal Lands Trust, the landowner, and I guess our spiritual partners on site. So I didn't want to say too much more, other than the fact that probably my main concern, for obvious reasons, is that we're a little bit long on Canterbury grads. We're a bit light on Auckland grads. So, if there's grads listening to this and you're from Auckland, we'd like to hear from you. We're overloaded with Canterbury mongrels. But genuinely, we think we're on a super exciting journey. This is, I guess, engineers coming together across disciplines and doing, really, genuinely really exciting things. And that was all I really wanted to say. I can't hear anybody, actually. Just a bit awkward.
Yep. Sorry, repeating the question, what are the challenges in the engineering capability in New Zealand to deploy a large-scale hydrogen production?
We seem to have just got the main room back. Can you hear me? Cool. Most of the widgets involved in hydrogen production are pretty common to the oil and gas and petroleum sectors. The biggest hurdle we've come across is on the compliance side, where we're trying to put hydrogen transportation use into regulations which are designed for industrial gas. So trying to put it in fueling stations and using new materials, composites, that sort of thing. So I think we have the skills in New Zealand, to, in the discipline engineering to manage that. It's really compliance and slight adaptations to what people do for the sector.
And possibly the last question for tonight, I'll leave it open to whoever can jump in first. How do we achieve a change in behavior and personal values to achieve the sustainable outcomes?
I'll have a go at this. Everybody should read The Rare Metals War by Guillaume Pitron, where we've effectively outsourced a lot of our dirty production to parts of the world that we don't care about so much. So, taking ownership of our energy production and our minerals production and all those things is ultimately the only thing that will drive consumption patterns, because then we will care about the environmental impacts of those things. And that will deeply engage every one of us in the genuine costs of energy and mineral use.
I want to jump in.
I could very quickly. From my time at ICA, thank you. From my time at ICA, where we not only have engineers but a wide range of other disciplines as well, behavioural scientists and marketers, which are people that engineers actually aren't that familiar with working in. It just feels like advertising and research are actually incredibly important for how you tailor your messages in order to reach your audience. So if there's one thing that I would do, it's for engineers to work more in an interdisciplinary way with non-traditional partners such as marketers, market research and behaviour change scientists. And I think that's the way that you can help get the messages that you need across to people to help with that behaviour change.
All right, I guess I'll come up. Thank you to all of the speakers, both online and here in Wellington, and thanks to everybody for joining us. It's been really good to start to see. I'm going to have to move. I'm going to have to jump over this way. Good to see and hear all of the things we're doing, whether it's the advice to the government from the Climate Commission and what the view is on getting us to carbon neutral for New Zealand and even beyond, but also all of the good activities by which the engineers around here are involved in decarbonising or concerned with the minerals and just generally managing our sustainability. I think for me the challenge I would give all of us as engineers is to continue the conversation, continue working together, continue talking to each other and moving forward. We have a role to play in designing and implementing sustainable solutions and also helping to support the adaptation of those solutions so we can make those solutions easier. I really like the idea you had of creating a new terminal that changes the commute for people in Miramar. That helps support that now sustainable solution, and even if it has a cost increase, you now created a whole new mode of transport for people. So that thinking that way really helps them, I think, with the adaptation. And also aligned with what John Worth was saying is thinking about the whole life cycle. So let's not take a carbon and emission problem in New Zealand and make it a carbon and emission problem somewhere else. But also think about that and also what waste are we creating and what other issues are we going to create. So let's not try to solve this problem by creating one that we'll see in the future. So thanks again. Thanks very much to the organisation group. So we've got Hugh and Greg, as well as Kirsty and Tash, and a huge thank you to Kirsty and Tash for managing all of the details and for Richard for introducing. So thank you.